This meeting is being recorded.
So, good afternoon, everyone. It's a pleasure to have with us Professor João Rodrigues from the Federal University of Pará, UFPA, in Belém, Pará. In addition to his teaching research activities in the area of elliptic partial differential equations at UFPA, Professor Rodrigues currently holds the position of Regional Secretary of the Brazilian Mathematical Society, SBM. So I would like to thank Professor Rodrigues for accepting the invitation to participate in this event, where he will present the lecture, The Method of Nehari, Manifold on Cones. So, Professor Rodrigues, the stage is yours. Thank you very much for being here.
Thank you, Sandra, for the introduction. Before starting my talk, I want to thank the opportunity to be here. For sure, it's a great pleasure for me. The second time I'm participating of this seminar, and in this occasion of the 100th session seminar. I'm glad to participate. Thank you very much for the invitation, Juan, Diego, and Ana. Okay, so the work I'm going to talk about was made in collaboration with the Nilson from Federal University of the Campina Grande, my PhD student, João Felipe. And here we are going to talk about the method of the Nehari manifold on cones. Okay, so the first paper studying this class of problems was in 1960, where Nehari was interested in studying this class of ordinary differential equations and or second order ordinary differential equations under some specific boundary conditions like this one. And the main idea of the paper of Nehari was, okay, I will associate an energy functional to this equation, but I will consider some specific constraint to this functional. So this constraint was this one, given by this equality in the last line of the slide. And the good thing about this constraint is that in a natural way, you can see that if this functional has some critical point, so this critical point will be in this constraint. Okay, if y is a critical point for the functional I, so you can see that the critical point y will verify this equality in the last line. Okay, so the idea introduced by Nehari was very interesting, and in the following years, this idea turned out very useful in a lot of situations, different situations, and many authors started to use the ideas of Nehari. So let me tell you some words about this approach is today known as the Nehari method, and the classical approach we can use in order to follow the ideas of Nehari is following these steps. For example, if you have a function, a C2 functional defining some Banach space, so we can define an appropriated set like this one, set N, in which we consider all the functions U belongs to the non-trivial functions belong to the Banach space with verify this equality. Okay, so as I said before, you can see that if U is a critical point of functional Y, so U belongs to this set. So this is a very natural constraint because if you want to looking for critical points of the functional I, you can look at your functional restricted to this set because all the critical points are here. Okay, but under appropriated assumptions of on the Banach space, you can prove using, for example, the classical implicit function theorem in Banach space that this set has a differentiable structure in the sense that this set is a C1 manifold of codimension. Okay, this is a very classical standard step, and this is possible if you have good properties in the norm of your Banach space. Okay, and because your functional is of C2 class. Okay, the next step is if you minimize your functional on the set N, and the more technical step is to show that your minimum point on the set N is a critical point of your functional defined in the Banach space. So since we have a differentiable structure to the set N, you can use the Lagrange multiply theorem to prove that minimum points of the functional I on the set N are critical points of the functional I. So this is a sketch we can use in order to follow the ideas of Nehari. But a good question now is, and what happens if my functional is only of C1 class? So here we cannot prove, it's not true that your set has a differentiable structure in this case. So you cannot use the implicit function theory in order to prove that your set is a C1 manifold. So the last step is very difficult to prove because when you use the Lagrange multiply theorem, you are using this differentiable structure. So this question is very interesting, and in this paper, in 2009, Zulkin and Wave considered this situation. Okay, the idea in the paper of Zulkin and Wave was to study some Nehari and Pankov method to some functionals of C1 class, and we have many applications if we consider functionals of C1 class, because this means that when you can consider, for example, some elliptic partial differential equations with the right-hand side involve some nonlinearity, only continuous nonlinearity. Because in this case, when you look at the energy functional associated to this class of problems, so your functional is only of C1 class. Okay, so this is a very interesting topic to study, and in the paper of Zulkin with the authors requested the following assumption for the functional. So we will call this map for it U, a non-trivial U belonging to the Banach space, and for it positive P. We will define this map, which is known as a fiber application. Okay. And the authors requested that this map has a unique critical point, which is a global maximum point. Okay, so if this is happening for all U different from zero, belonging to the Banach space where the functional is defined, so they could prove that there exists a homeo. Okay, in this case, since the functional is only of C1 class, your Nehari set has not a differentiable structure. But if you have this assumption 81, you can prove that the Nehari manifold, the Nehari set, is homeomorphic to the unity sphere of the Banach space. And if you have some additional assumptions on your Sobolev space or your Banach space. So you can prove that the unit sphere has a C1 structure. The unit sphere is a C1 manifold. So you can use the differentiable structure of the unit sphere in order to overcome the problem of prove that critical minimum points of the functional on the Nehari set are critical points. So the main contributions in the paper of Azuk and Webb were a topological study of the Nehari set in order to find and prove the existence of ground state solutions under assumptions of some assumptions on the nonlinearity, as the nonlinearity has a superquadratic growth at infinity, for example, and a new characterization of the minimum level on the Nehari manifold, the minimum level of the functional on the Nehari manifold, as this one. Okay, but I would like to show you some very simple prototypes of partial differential equations in which the hypothesis 81, as considered in the paper of Zook and Wave, are not satisfied. Is not satisfied. So, for example, if you consider this equation where the function 8 is a L infinite function, and this is changing sign because the positive and the negative part are different from 0. Of course, here, just for consider a simple case, we will consider that the power P is a subcritical power, okay? So, I is the energy function associated to this equation in this case, and we can see that if we define this set A composed by all the functions U belong to the Sobolev space where this integral is positive, okay? So if you consider all the fibers for functions U belonging to this set, so the behavior of the fiber is exactly as in the hypothesis 81 as requested by Zook and Webb. But if you consider some function U outside of this set, so the fiber has no critical points. So this is a very simple example of a problem, of a very simple problem in which the hypothesis 81 is not satisfied for all function U different from 0 in the Sobolev space. So we couldn't apply the method of Nehari as presented in the previous paper of Zook and Webb. So another example I could mention here is this one. Here we are considering a different function. For example, he is not necessarily a power. Here we are considering a function satisfying some conditions at 0 and at infinity. For example, some kind of how can I say some behavior at infinity, like asymptotically linear condition at infinity, okay, and at 0. So in this case, if we control the size of number alpha and eta in order to compare with the first eigenvalue of Laplacian operator with Dirichlet boundary condition, homogeneous Dirichlet boundary condition, and this another hypothesis is this function is increasing. So we can show that the hypothesis 81 is not occurring in the for all function different from zero in the space. For example, let's consider the functional I associated to this problem. And we can see that for each positive t and u different from zero, so this limit is strictly positive because the number alpha by hypothesis Fe1 is less than the first eigenvalue of a Laplacian operator. Okay, so this is telling us that near to zero, the fiber is positive. Near from zero, the fiber is positive. But on the other hand, if you look at the behavior of this function at infinity, so since we have the limit is equal to this number, in order to provide the geometry of hypothesis 81 in the paper of Zook and Webb for some u different from zero, is important to consider this set A, this open set A, composed by all the functions with verify this inequality here. Because if I have some function u belonging to this set, so when I take this limit, I have that this limit is negative at infinity. So, and I will have that the fiber for all u belonging to set A has a unique global maximum point as requested in the hypothesis of Zook and Webb. But if u is not belonging to this set A, so we can prove that we don't have critical points to the fiber. This is exactly what is happening in this very simple calculation here. And we can see that in this another example, we don't have hypothesis 81 for all u belonging to the Banach space, to the Sobolev space. And just to finish the examples I'm providing here, in order to justify that it's important another kind of a weaker hypothesis in order to cover this class of problems. Let me tell you some words about this problem here. So here I have this problem where the parameter lambda is less than lambda 1. Okay, and here we will consider the energy functional another time associated to this problem. And if we consider this open set A, so we can see again that for functions belonging to this set, we have a unique global maximum point, but outside of this set, we don't have critical points for the fiber function. So, okay. Let me tell some words about this work published in 2021 by Figueiredo, Curran, and Silva. In this paper, the authors studied some problems involving functional with different behavior for each fiber. Okay, so in some fiber, for example, you have 2 critical points. In other fiber, you have just 1 critical point. But several abstract results were provided in this paper in order to get existence of ground state solutions over open cones. Okay, so more specifically, the authors are interested in studies this type of functional given by the difference between 2 C1 functionals, and in some moments the authors investigated what is happening if for all U belonging to some open cone V in the space, you have only one maximum global point. So under this type of assumption, the authors were able to prove and provide some abstract results of existence of critical points. For example, many applications using these abstract results were made in order to study some homogeneous and non-homogeneous operator like Kirchhoff operator, PQ, Laplacian operator, some systems also. And but in the particular case for which the hypothesis A21 is satisfied only in the open cone, the authors are not concerned with the study of the topology of the Nehari set in order to answer some questions like if we don't have the hypothesis H1 for all function belonging to the Banach space, as in the work of Zuckerberg, and if we have H1 only for an open cone of the Banach space, in this case, can we prove that the Nehari set is yet homeomorphic to some C1 manifold of the Banach space? So this type of questions are open even after this paper, and the authors was not concerned with this type of questions. So the main goal of this talk is in this direction. So our main goal here is to answer this kind of question: is the Nehari set homeomorphic to some other set if we don't have the hypothesis H1 as in this Zuckerberg paper? If so, what is this set? This is the question. And is this set a C1 manifold? So, okay. In this work, we will give him a positive answer to these questions, and we will show, in fact, even if we don't have some hypothesis as in the Nehari, in the Zucken and Webb paper, so we can prove the existence of a homeomorphism between the Nehari set and a very particular C1 manifold of the space. Okay. Let me present you some assumptions we will consider here. So this first assumption was considered in the paper of Zuckerberg. This assumption is a condition on the Banach space we are working, and here basically is to guarantee that the unity sphere of the space is a C1 manifold, because here we are requesting the existence of a normalization function for which the composition of the primitive of the normalization function with the norm of the space is a C1 function. So if this is the case, we can prove that the unity sphere of the space is a C1 manifold of codimension 1. Okay, so this is not new. This was requested in the paper of Zuckerberg. But the second condition we are considering here is more general than the condition 81 of the paper of Zuckerberg. For us, now the fiber doesn't need to have only one critical point for all function u in the Banach space. For us, all you need is the existence of an open cone. And for us, a cone is a set verifying this equality here. Okay, so we need the existence of a set verifying this equality for all positive t, and for all function u belong to this set. We are requesting the existence of a unique maximum global point for the fiber. Okay, and if u is not belonging to this set, so the fiber has no critical point. So under this assumption, we were able to prove the existence of a homeomorphism between the Nehari set and the C1 manifold. We will show later on. Okay. Okay. The last assumption is some assumption involving the maximum point of the fiber, which is we will denote for by TU. Okay, so TU is greater than or equal to some positive constant for all U belong to SA. Just a remark here. Since we have the hypothesis A2, we can prove that the intersection between the unit sphere and the open cone is non-empty. Okay, and we can denote the intersection between the set A and the unit sphere as SA. This is a C1 manifold because the unit sphere of the space is a C1 manifold. Since we are requesting the hypothesis A1, and we will prove that our Nehari set is homeomorphic exactly to this set SA, to this C1 manifold. In this case, it's very important to realize that this is not the whole sphere, unit sphere, because in the great part of the applications we made here, A is strictly contained at the sub-level space. Okay. Okay. This is a very important lamp here because we can prove some topological properties of the Nehari set. For example, the Nehari set is closed and is the distance of the Nehari set to the origin of the space is strictly positive. Okay. Of course, if I have the assumptions A1, A2, and A3, we can prove of we can go to the next frame. So this is a very technical part of the work, because here we can establish the existence of the homeomorphism between the Nehari set and the C1 manifolds SA. So we can define this function M as the restriction of M hat to the set SCA. So you can prove here of this function M is a homeomorphism, and we can show exactly who is the inverse of function M in this case. Okay. Okay, this is the geometric idea of the problem. Here we have the unit sphere of the Banach space, and here we have the open cone A, and the intersection between the unit sphere and the open cone is the set SA, our C1 manifold. And here we have the Nehari set. So the Nehari set is not, in this case, since we are working with C1 functionals, so the Nehari set is not a C1 manifold, but we can prove the existence of a homeomorphism even if the hypothesis A1 requested by Zook and Weff is not occurring. Even in this case, we can prove the existence of homeomorphism. But here we have some technical difficulties because the new C1 manifold, which is homeomorphic to the Nehari set, is not a complete manifold as the unit theory of the space. And in the applications, we have that when we consider minimizing sequence in this C1 manifold for functional I, we have take care about the boundary of the manifold. So it for us is a problem if the sequence, the minimizing sequence are going to the boundary. We have to control the behavior of minimizing sequence near the boundary. Okay. The main abstract result is this one, which defines C1 functional on the C1 manifold as A, and we can prove some relation between the energy functional associated to the problem and another functional psi defined in the C1 manifold as A. So, and some relations are observed between these two functionals, as for example, if you have some critical point of the functional psi, so and you apply the homeomorphism M in this critical point. So the M of U, if U is the critical point, M of U will be a critical point of the functional I. So this type of relation is very important because we can overcome the fact that the Nehari set doesn't have a differentiable structure. Okay, so we can provide some applications to this abstract result. For example, if we consider, I have a few minutes, so let me tell you just some words about this application. For example, if you consider this type of equation, here you have an integral term with turns this type of problem very, very difficult because we don't have comparison principle or some maximum principle where when the parameter A is large, for example, and we have problems to get a priori bounds for solutions of this problem and to determine the sizing of the solutions. So we have a lot of papers studying this class of problems because this class of problems model from situations in mathematical biology. And let me show you some. Okay, here. Okay, we are interested here with this particular case of that problem. Okay, when I have the Laplacian operator here, and I have the integral of a function u multiplied by a parameter a. So here we will consider this kind of nonlinearity where this function g is satisfying these two conditions, G1 and G2, okay? So If this is the case, when we look at the ET fiber of the energy functional associated to this problem, we can see that we don't have a unique global maximum point for ET fiber belong to the sublab space where we're looking for weak solutions of the problem. In fact, if we consider this norm of for the sublab space, so this will be the energy functional associated to the problem, and the Nehari set is this one, NA. Okay, so we can see that if we define this open cone as this class of functions which has this power, the integral of this power is negative. So this open cone satisfies the hypothesis A2 we have imposed in our abstract result. Okay, and we can prove some technical results in order to show that we have the hypothesis 81, 82, and 83 in our case, and that this second proposition is to control the behavior of minimizing sequence near the boundary of the set SA in this case. Because if we consider, if we have this condition, so we can see that minimizing sequence are not going to the boundary because if the distance of minimizing sequence to the boundary of set SA is going to 0, so in this case, the functional psi applied at the terms of minimizing sequence is going to infinity. So this is not possible because minimizing sequence, for minimizing sequence, psi applied in the term or in each term of the minimizing sequence is bounded. So this first item is just to control the behavior of minimizing sequence near the boundary of set SCA. Okay. Okay. So we can prove our main result regarding to this problem, which is if the parameter A is small enough and the parameter lambda is less than the first eigenvalue associated to the integral differentiable operator we are considering here, and function the nonlinearity G is satisfying the hypothesis G1 and the G2. So the problem has a ground state solution, which is a Eigen change solution. This is changing his Eigen, or is a negative solution. Okay, so okay, here we have some steps of the proof, which consists in mix some results involving our abstract result and the previous propositions we have showed here. And in this work, we have presented many other applications, as for example, other kind of problems, but I don't have time to present here. So let me, to finish the presentation, let me say some words about we think that other applications are possible. We have studied some other problems involving Kirchhoff operators and some other kind of quasi-linear problems, but we think the range of applications is very interesting for this method. So I don't have time to show. Thank you very much for your attention.
Thank you, João. Now we have time for some questions or comments. Please, if you want, you can write in the chat or talking using the microphone. No, João will open the microphone for the questions.
Hello, Sandra. May I ask a question?
Yes, Diego. Okay, please.
Okay. Congratulations, João, for your very nice talk. I wonder if the method that you present is extendable to systems of elliptic equations.
Oh, good question. Good question, Diego. I think so. I think so. Uh, if you have a system which is we can associate energy functional in order that critical points of the energy functionals are weak solutions of the system. If you can do that, so I think under appropriated conditions, we can apply our method for systems. I don't see problems, important problems, because the fact we have a system now and not any. Sorry.
Because in your method, you do not require a comparison principle, right? Or
No. In the first application of our method, the particular problem we are considering that don't have a comparison principle.
yes,
But yeah.
and this is interesting because normally for systems you do not have comparison principle.
Okay.
So that would be interesting to analyze the case system because there are very few results.
So this is interesting. We didn't apply for systems in the paper. We didn't apply our method for systems, and I didn't think about that. So this is a very good question, a very good idea. Maybe we can think about a little bit.
Okay. Good. And another question is related to because you treat a bounded domain, right?
Yeah. All the applications were for bounded domains. Yeah.
What about unbounded domains or stereo domains or other kinds of?
Okay. For the abstract result, we are not using some kind of how can I say, compact embedding or something like that. So would be a problem for unbounded domains, for example. So I think we can study problems involving unbounded domains, but with appropriated assumptions on the nonlinearity, and so in order to put the problem in the conditions we are considering the abstract result we are present here. So I think it's possible in some situations for unbounded domains.
Okay, thank you very much.
Thank you, Diego.
Okay, Diego, thank you. We have another question in the chat. Professor Massoud writes that, thank you, Professor, for interesting lecture, and I have a question. Can we use this method in case of the eigenvalue problems where lambda is not a simple parameter but an eigenvalue? Thanks.
Okay. In the case of lambda is exactly an eigenvalue of the...
It's not a simple parameter, but an eigenvalue. Yes.
Okay, for... I don't know if I understand the question, but for the eigenvalue problem, for example, involving the Laplacian operator with Dirichlet boundary condition, we don't need to use this method. But this, how can I say? Here, I think I don't know if I understand the question. So this method is I'm sorry.
Okay, Massoud, Professor Massoud, can you speak? We are with the audio open, if you prefer.
Good afternoon,
Okay.
Professor. Can you hear me?
Yes.
Okay, thank you. what I meant by an eigenvalue problem is that the problem you discussed in the end.
At the end.
Yes, here.
At the end, okay.
The problem
Okay, this
P1,
one?
I think.
P1, let me see the other one, this one?
Yeah, it's the same. Here, if we take lambda an eigenvalue.
Ah, okay, I understand now. Thank you.
Thank you so much.
If lambda is an eigenvalue, I don't know. Here.
Okay, thanks. Because we use.
Yeah. It's important for us that
Logistic Schnellmann theory and C1 manifolds in the case of eigenvalues problem.
Yeah, for us, for example, the fact that if lambda is greater than lambda 1, so the geometry is completely different now, because now, for example, the functional has another kind of geometry, like the origin of the space is a saddle point now. If lambda is greater than lambda 1 of A, so I think that in the case that lambda is exactly equal to lambda 1 of A, so in this case, we don't have the geometry we need in order to prove that all the fibers belong to the open cone have a unique global maximum point. So I think I'm not sure if in the case of lambda is equal to lambda 1, we can apply the method, because I'm sure that if lambda is strictly greater than lambda 1, it's not possible. It's not possible here, because we need some kind of a Pankov approach, like a generalized Nehari manifold. In this case, in the case lambda is greater than lambda 1, but in the case that lambda is exactly lambda 1, I'm not sure. I need to think about that.
Okay, thank you so much for your answer. Thank you.
So thanks again, Professor João Rodrigues, for being here to have this very nice lecture. So maybe we have you here in another opportunity.
Oh, thank you very much, and congratulations for the seminar. Thank you.
Okay.